Audio Jungle.
Oi! Hello everyone! I am Janina, Kathleen, and Roseanne, and we are here to discuss the theory of relativity by Albert Einstein. First, we will discuss about relativity of simultaneity. Sa mga ikilala, let's watch this. Here is the example of relativity of simultaneity. Two events simultaneous for one observer may not be simultaneous for another observer if the observers are in relative motion. Parang ganyan lang. Yung nasa loob ng sasakyan, ang feeling nila steady sila at yung paligid nila ang gumagalaw. Pero itong observer na to na nakatayo lang, ang alam niya, ang paligid ang nakasteady at ang sasakyan ang talagang gumagalaw.
Imagine two observers, one seated in the center of a speeding train car, and another standing on the platform as the train races by. As the center of the car passes the observer on the platform, he sees two bolts of lightning strike the car, one on the front and one on the rear. The flashes of light from each strike reach him at the same time, so he concludes that the bolts were simultaneous, since he knows that the light from both strikes traveled the same distance to his eyes at the same speed, the speed of light. He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear. But what does the passenger see? As her friend on the platform predicted, the passenger does notice the flash from the front before the flash from the rear, but her conclusion is very different. As Einstein showed, the speed of the flashes as measured in the reference frame of the train must also be the speed of light. So because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first. Whose interpretation is correct? The observer on the platform, who claims that the strikes happened simultaneously, or the observer on the train, who claims that the front strike happened before the rear strike? Einstein tells us that both are correct within their own frame of reference. This is a fundamental result of special relativity. From different reference frames, there can never be agreement on the simultaneity of events.
So ayan, napanood na natin. Naintindihan mo ba? Pero naintindihan mo. Ay, kayo ba naintindihan nyo? Uy, ako naman! Let's start with
time dilation. Moving clock or measures to take more slowly than stationary clock. Parang ganyan, yung nasa loob ng sasakyan, nila tama lang yung pasunla. Bossing, manalas game PH pa lang! Takpa natin! Pero sa observer na nakasalulang, ang bilis-bilis ng takbo ng sasakyan na yun.
Grabe, ang bilis sila, mga makasali sila!
Yan ang time dilation.
One of the most unusual consequences of the speed of light being a constant for all observers is that the flow of time itself is not immutable. It too must be relative to the inertial frame's motion. Here's a good way to see why this must now be the case. Here's a simple light clock. Light travels between mirrors at the end of a known length. For our purposes, we'll make it a very long length, say 150,000 kilometers. That way, one round trip will mark 1 full second. Now, if we put the clock into motion with respect to a ground-based observer, we see that the light has to travel further. And because its speed is constant, it will take longer. The moving light clock is therefore running slower than a stationary duplicate. This is called time dilation. It's the geometry of the situation that gives us the conversion factor. If I were on a 10-hour flight from LA to Paris, traveling at 800 kilometers per hour, I would lose just under a nanosecond. Way too small to notice. But for faster moving spacecraft, it can be quite significant and critically important. For example, orbiting GPS satellites travel at 3,874 meters per second with respect to the Earth. They use cesium atomic clocks to keep time. They measure time to within 1 second in 1,400,000 years. But these onboard clocks lose 7,214 nanoseconds a day due to time dilation. If onboard clocks aren't corrected regularly based on Lorentz time dilation formula, the position data they produce will be off by kilometers in less than a day.
Ayan, nakatapos na tayo. Naintindihan niyo ba?
Easy lang.
Hello, naintindihan niyo ba? Oh, teka lang. Hindi ako papahuli. Meron pa tayong length contraction.
Length contraction. Objects are measured to be shortened in the direction that they are moving with respect to the observer. Parang yung trend na yan, nagiging maikli sa paningin natin dahil sa sobrang bilis ng takbo nila.
Think about what that means. Here's a little ruler. It's 1 foot long. And to within experimental accuracy, I and every physicist who's in my reference frame will agree that this ruler is 1 foot long. Now, how about a physicist who's cruising by at some high speed past me in an inertial reference frame, they're not accelerating, and they measure the length of this ruler? Will they agree with me? If they agree with me, then all observers agree, and we would say that length is an absolute. And if they disagree with me, then we would say length is relative. And indeed, that's the way nature works. It's bizarre, but a moving physicist who measures the length of this ruler will conclude that it's a different length. It's shorter than 1 foot. We call that length contraction, relativistic length contraction. Strange.
Oh, nakita niyo ba yun? Oo. Naintindihan niyo ba? Oo naman, siyempre. Ito.
Uy, wait lang. Isa pa natitira. Yung maximum speed. Let's watch this.
Maximum speed is finite. No physical object, message, or feed line can travel faster than the speed of light in a vacuum.
Put aside, can we go faster than light? Well, in a vacuum, that doesn't really seem to be the case. However, in different mediums, like glass and water, light travels at slower speeds. Due to its slower speed, it is possible for some particles to beat light in a race when it's going through certain mediums. In fact, when this happens, Chernikov radiation can occur. Named after Pavel Chernikov, this type of radiation can be seen as a bluish-white glow in places like the pools of water that surround nuclear reactors. In these instances, electrons from the reactors are moving through the water faster than light is moving through the water, creating what we see as the faint blue glow. It's similar to a sonic boom, but with light instead of sound. Going faster than light in this way is kind of like having Usain Bolt wear iron boots so that you can beat him. But hey, a win's a win. It's also interesting to know that a few years ago, researchers in Scotland were able to slow the speed of light traveling through free space. Like we said before, we already knew that light could be slowed when it moved through things like water and glass, but they found that they could slow photons moving through free space. They did this by applying a mass to an optical beam that gave photons a spatial structure to reduce their speed. While the difference they were able to measure was small, hopefully this could lead to some pretty awesome discoveries one day, and help us better understand light. But just for fun, if we could find a way to travel at the speed of light, what are some things that might happen? Well, there would probably be some complications, like running out of fuel rather quickly, or having a hard time avoiding space debris when going at that high of a speed. Also, due to time dilation, if you went on a mission in space going at the speed of light, when you got back to Earth, your loved ones relative to you would have aged more. If you did it for long enough, they could even be dead. And that's pretty scary to think about. Let's move on. If we could travel at the speed of light, it would certainly open us up to some amazing opportunities. Besides just being able to get to school or work on time, we'd be better equipped to try and colonize other worlds. Going at the speed of light, we could reach Mars in under 30 minutes. We could also reach TRAPPIST-1 in the span of one of our lives, as it would only be about 39 years away. If you haven't heard of TRAPPIST-1 yet, it's a planetary system with the most Earth-sized planets found in a habitable zone of a single star. Finding a way to get there could be a great leap for humanity expanding itself to other worlds. If you could travel at light speed, where would you go?
Ayan, naiintindihan niyo ba?